Hello, welcome to Machine Learning webinar series. In this episode, we are going to mention automated machine learning, AutoML concept, and we are going to develop the hands-on application with H2O AutoML. Let me introduce myself first. This is Shefik. I have been working as a software developer for a fintech company since 2010, and currently I'm working as a data scientist in an AI team here. I received my Master of Science degree in Computer Science from Galatasaray University in 2011. Moreover, I have a personal blog, cefix.com. I mostly share here machine learning related posts. Furthermore, you can contact me on Twitter, and you can find my open source projects on my personal GitHub profile. Imagine a successful neural network, and it's responsible for classifying cat and dog pictures. This structure has one hidden layer, and this hidden layer consisting of 4 nodes. You can question the design of this neural network structure. Common questions might be, for example, should I use neural networks in this problem, or gradient boosting machines could perform better? This is an algorithm based question. Moreover, you can ask why the network consisting of one hidden layer, why shouldn't it be 2 or 3 hidden layers, or why the first hidden layer consisting of 4 nodes, it could be 5 or 6, or activation function might be a question, it could be sigmoid or hyperbolic tangent. These are model based questions. Or you can ask some hyperparameters, for example, why the epoch value is 2000, or why the learning rate or learning time is set to 0.01. These are hyperparameter based questions. If you are going to build gradient boosting machines such as light GBM or XGBoost, hyperparameters are still questions for your design. In this example, number of boosted trees are set to 3000 and learning rate is set to 0.1. But why? Splitting data into train and test sets is an important action for your modeling step. For example, you could split your all data into 85% for train set and 15% for test set. Also, to avoid overfitting, you should split your train data into train and validation sets. In this case, you could split your train data to 70% of your all data, and validation data might be 15% of your all data, and test data remains same. On the other hand, we mostly use k-fold cross-validation for large-scale data sets. But all of those are not rules. Any data scientist can do anything actually. Decisions of data scientists are mostly based on their sense. Here, AutoML algorithms look for the best algorithm for your problem, best model for your algorithm, and finally best hyperparameters for your model. Also, AutoML algorithms split your data into train, test, and validation sets, and moreover, it finds the best cross-validation method, k-fold or any other thing. Now we are going to develop a hands-on application with H2O AutoML. H2O AutoML supports the following algorithms. Firstly, deep learning, but do not think convolutional neural networks. It supports regular multi-layer perceptron, and XGBoost, extreme gradient boosting, and its own GBM implementation. Moreover, random forest, linear models, and Finally, ensemble methods of all of those algorithms. Based on my experiments, I can say that ensemble methods would perform better than all of those individual algorithms, because ensemble methods combine all of those algorithms and finds the best solution. Firstly, I'm going to import the H2O framework. Normally importing the framework is enough in Python, but H2O gets a Java process up. That's why I'm going to initialize the H2O framework. Passing init command mostly works, but sometimes you need to specify some configurations. For example, your IP address, that will be your localhost. Then maximum memory size might be required. Also, number of threads would be useful sometimes. Then multiprocessing dot CPU count will give you the number of limits in CPU cores. For example, I can limit the number of threads to 2 because it's less than the maximum number of my CPUs. Also, you can decide the maximum memory size by importing psutil dot virtual memory will give you the available memory size. You can limit your memory based on these values. For example, I can say the half of the available memory will be my maximum memory size. But I have already initialized my H2O engine. That's why I just passed init command here instead of specifying the parameters. These blocks also could be in same cell. In this way, we can have a clear notebook. And this is the CPU cores, and these are the memory related information. I have already downloaded the dataset I'm going to use from this address, and it's on my desktop. That's why I'm going to import it. Firstly, I can import it with pandas, and pandas.read CSV and train true positive features, and these are my positive dataset, and similarly I have a negative dataset, and its name was true negative features.csv. It says PD is not defined. That's correct. I forgot to add here PD. Let's look at the first 5 rows of my dataset. It contains 2 persons similarity values based on VGG, FaceNet, and OpenFace face embedding models. Also, there are emotion based features, and some of features are not seen here. I can see the columns just like that. These are my columns. Here is related column is the target value I would like to predict, and these are the features I would like to use in my prediction step. I'm going to discard some features, for example person1 and person2 contains names, and I do not need these values. Also I'm going to use just phase embedding features, VGG cosine and VGG Euclidean, and its L2 normalized form. Let's define it in a list here. VGG cosine, VGG Euclidean, FaceNet cosine, FaceNet Euclidean, open face cosine, and open face Euclidean, and finally is related my target, and in this way it would be clean, and I can drop rest of columns like that. Data frame positive will be consist of just these columns, and similarly that's negative value will consist of just these values. Let's look at the first 5 rows, and as seen, that's my data set. It consists of 6 features and 1 target value. I need to convert this pandas type variable to H2O form. I mean that H2O dot H2O frame and passing data frame positive will convert it to H2O format, and I renamed it as HV positive, and similarly I'm going to apply it for negative values. First one is over, and I'm waiting for the second one, and it's over now. Now its type is H2O frame, whereas df positive type is pandas data frame. I have read the dataset with pandas, and then I convert it to the H2O frame format, but it's long process as seen. Instead of this, I'm going to restart the kernel, and here this block refers to pandas to H2O, and I set this to markdown. Actually I can read the dataset with H2O directly. H2O frame actually. I restart my H2O engine here, and HF positive is equal to H2O dot import file, and here I'm going to pass the same path, and similarly I'm going to apply it for -1. First one is over, and second one is over. As seen, this method is much faster than the reading it with pandas and transforming to the H2O format. I'm going to use same columns here. These are my flat columns, and I'm going to use same command here. And do it for the HV negative. Now let's see the first top rows for HF positive. These are my features and these are my target values. Target column consists of just once in HF positive, and in contrast HF negative consists of just 0 columns. I need to merge these two H2O frames. Actually, here I'm going to apply it, and it will be HF, and it's equal to HF positive dot row bind to the HF negative, and this is my HF frame, and I can see the content of HF. Its first top rows consist of related instances, whereas its tailed rows consist of 0 unrelated instances. I can see the details of the columns of HF dot describe. This will give the H2O frames columns. As seen, all columns are in real type, but is related shouldn't be it. It's actually class, because if it would be integer, then this is going to be a regression problem, but I would like to define this problem as a classification problem. To convert the is related column to the class, I need to apply this as factor. Now let's describe the H2O frame again. Now it's enum type. This means that I'm going to define the problem as a classification problem. Now I can build my model. It's going to be modeling step. I need to import the AutoML library from H2O.AutoML, and here import H2O AutoML. Normally I should split this dataset into train, test and validation sets to avoid overfitting. When you are going to build AutoML, you don't have to do it, because AutoML handles this, but you still do it. HF dot split frame ratios is equal to this expects list, and here I'm going to pass 80%. If this list consists of one item, then this is going to return train set and validation set, 2 items. If this list consists of 2 items, then this is going to return 3 items, for example train test and validation. To do this reproducible, you should pass a seed number, and it's my favorite, that's why I'm going to pass 17. Now is related is my target label. It's related, and I also need feature names, and I initialize it as a list, and let's build a for loop here for I in hf dot columns, and let's print the current column. Here I'm going to check the current column is not equal to the target label, In this case, I'm going to append this column to the feature names, and let's check the feature names. These are my 6 features. Now initialize your AutoML model, H2O AutoML. Optionally, you can specify some configurations to your AutoML model. For example, in the AutoML documentation, you can pass maximum runtime in seconds. Its default value is 1 hour. For example, I can say it should be 60 seconds, and 1 hour consists of 60 minutes, and let's run it for 24 hours. Or you can say build maximum 20 models, or you don't have to specify anything. I mostly specify maximum runtime seconds, but 24 hours is really long. That's why I'm going to run AutoML for half hour. It says it got a float value, but it expects integer. That's why I'm going to cast it to the integer. Now it's time to start your AutoML model. As seen, it expects X and Y. X and Y actually feature names. I store it in target label and feature names variables, and also training frame and optionally validation frame. My training frame would be train, as you might remember, and X values are feature names, and Y values is my target label, and I can start my AutoML model. And as seen, it started. It runs for a half hour. Hello again. Training is over as seen. AutoML built several models. Let's check them. AutoML.leaderboard. As seen, there are almost tens of models, and the most successful one is stacked ensemble model. It's actually a combination of some GBM and linear models here. I can get the most successful model, AutoML.leader. That would be my model. And let's check my model here. H2O offers very detailed model details here. For example, here are training data metrics, mean squared error, root mean squared error, and this is the confusion metrics for my train set. And here for cross validation data, remember that I just passed the train set here, and it splits for my train set into train and validation data, and this is the validation data metrics, mean squared error and root mean squared error here. Here is the confusion metrics also. Remember that I split my data into train and validation sets, and AutoML doesn't know this validation data. Let's check the model for this validation data. Model performance, and I'm going to pass validation data here, and that will be my performance. Let's see the performance variable here. root mean squared error is equal to 0.44, and in my model, let's check the validation data's root mean squared error. It's actually similar, not same, but it's close. This means that we can build a robust model. When you believe that your model is robust, you should save it. H2O dot save model, and I'm going to pass my leader model here. Also, path would be the same directory of this notebook, and finally force should be true. That would be my saved model. You can see where the model saved and what's the name of the file. Now it's time to prediction. Set this block to markdown. Model should have predict function, and here I'm going to click shift and tab buttons, and here validation will be my testing data, and I'm not going to pass custom metric and custom metric function here, and store the result of predict function to the predictions. You can see the predictions. As in, there are 3 columns. First column is the most dominant class. For example, here P0 means the unrelated probability, and P1 is equal to related probability. If you need just the prediction class, you should use predict column. Otherwise, you might need class probabilities. In this case, you can use 1 to the end. This returns the probability of each classes. Here, predictions object is in type of H2O frame. Let's check it. We can convert it to the pandas here. As data frame function under the H2O data frame transforms your H2O frame to the pandas. I'm going to use predictions pandas variable. Now also I can check the type of predictions pandas. It's pandas data frame. For example, you can check the prediction for example 17 index. It's actually predicted as related, and these are the probabilities. So we have mentioned AutoML concept and daily application of AutoML with H2O AutoML. It's a very successful framework actually, in particular tabular data based problems. But you are going to work on image based data. You should think to work with another AutoML solution. For example, AutoKeras would be fine for image based data. As seen, we skipped all designing steps, the algorithm, the model, its configuration. All of those are important things in machine learning designing, but AutoML handles them. You might realize that the key point here is the time of your training. For example, here we'll limit the building models with half hour. The longer time you provide, the better it is. So we have mentioned AutoML concept and developed a hands-on application with H2O AutoML. Thank you all for your attention. I hope you enjoyed the content of this webinar episode. Hope to see you in the next time.